Hello, welcome back for chapter 10. So if you recall, back in chapter 9, we learned about hypothesis testing and deciding if a particular outcome resulted in something that was unusual enough for us to say that what we think about the population is really not true. So now in chapter 10, we are going to work with hypothesis testing, but it's all about two samples. So first we need to look over what is independent sampling. It's when the individuals selected for one sample do not dictate or have a relationship with the individuals in the second sample. And dependent sampling. Dependent sampling, we're also going to call that matched pair samples. When the individuals selected to be in one sample are used to determine the individuals in the second sample. Okay, I also want to keep reminding you that in our notes packet that there's a link in the modules that you can print out. There are formula sheets for the testing of these different things. And the testing on these are labeled here. So testing regarding a population proportion, and then regarding the population mean. And then this is a chapter 10. This is about two population. There's some confidence intervals. And then chapter 10, two proportion. This is if you're using the, we're gonna not do it by hand. We're gonna just do it with printouts, but you could use a TI-84. The difference in two means there's a matched pairs. We're going to do this in Desmos. And then we're also going to do the two sample t-test in Desmos. Okay. Wanted to remind you about that. Okay, so example 1, it says decide whether the sampling method is independent or dependent sampling, then determine whether the response variable is qualitative or quantitative, because that's going to give us some information about means and proportions. So we conducted a survey of 100 random men and 100 random women to find out which was their favorite Summer Olympic sport to watch on TV. So they are independent, they're not married or anything, so this would be independent. And the type of their favorite Olympic sport is definitely going to be qualitative. There's nothing that we can measure numerically. So this would be proportions, is what we would be looking at. Qualitative tells us that we're looking at proportions. Letter B says, we conduct a poll of 100 random men and 100 random women to find out whether they like watching the Olympics on TV or not. We first call them the day before the games start, and then we conduct a follow-up call the day after the Olympics end. Okay, so this is dependent because we're comparing a before and after. And if they like watching it or not is still a qualitative variable. A researcher wants to know if basketball or soccer players weigh more. A random sample of male college basketball players and a random sample of male college soccer players were obtained and weighed. Then the results are compared. So there are different groups of sports, basketball and college soccer, so they're definitely independent. And we're measuring weight, so that is going to be a quantitative data variable. And so we're going to be comparing means. Quantitative is means. And then D, a researcher collected data showing the heart rate beats per minute for a random sample of coffee drinkers before they drink coffee and also 15 minutes afterwards. So this is a before and after. So this is dependent data. And it's quantitative because we're measuring beats per minute. So that's what we have to think about in chapter 10 is, are we talking about independent or dependent data? And are we measuring qualitative or quantitative variable. Okay, so 10.1, just a heads up, we're not going to be looking at 10.2, but we are looking at 10.1. It's two population means with unknown standard deviations. And so because they're unknown standard deviations, we're going to be using the t-distribution and Desmos. Okay, example 1 says, decide whether the sampling method is independent or dependent, then determine whether the response variable is qualitative or quantitative. So let's look at a couple more examples on this. A study wished to compare traditional acupuncture with usual clinical care for a certain type of lower back pain. The 241 subjects suffering from persistent non-specific lower back pain were randomly assigned to receive either the traditional acupuncture or the usual clinical care. The results were measured after 12 months of treatment. So because you didn't get both, you got either the acupuncture or the usual, it's going to be independent samples. And it's definitely quantitative because they're measuring the pain. Pain level measured. Okay. B says, we want to test whether there is a difference in the body temperature of men and women. We collect a random sample of 65 women and 65 men and take their temperatures. So again, they are not related to each other, so they're independent samples, and we're measuring temperatures, so it's quantitative. And last but not least, a recently published article reported the results of an experiment on reducing the percentage of men who develop prostate cancer. The investigators randomly assigned 3,305 men to receive the drug dutasteride and assigned 3,424 men to receive a placebo. Of those that received the drug, 659 developed prostate cancer. Of those that received the placebo, 858 developed prostate cancer. So they are definitely independent because you either received the drug or you didn't. But this is a qualitative variable because it's just a yes or no whether or not they actually developed cancer. So it's not quantitative, it's just qualitative. Okay. So example 2, I'm going to show you some printouts because we haven't really done a lot of using printouts of other computer programs, but there are statistical programs out there that you might use if you go to your PhD and you have to perform some statistics, or if you're in such a job. One of them is called StatCrunch. The other one I'm going to show you is Minitab. They give similar information, so we're just going to see the differences between them today. On example 2. So it says, many baseball fans hold that because of the designated hitter rule, there are more runs scored in the American League than in the National League. A researcher for ESPN gathers data on the number of runs scored per game on a random sample of American League teams and a random sample of National League teams for the 2006 regular season. So the American League can have a designated hitter to where somebody else hits instead of the pitcher. And so they think that maybe they score more home runs. So it says, verify that the requirements needed to conduct a hypothesis test were met. Okay, so if you get out your 2 sample, it's your very last page, page 306 in your formula packet. This is section 10.1. So we're testing the difference of 2 means independent samples. So in Desmos, so here are what we have to make sure that we have requirements. So do we have simple random samples? They did say they had a random samples, so we do have the simple random samples. The second is, are they independent of one another? So yes, independent of one another. Oops. then we have to show their independence, that they're smaller. They're each smaller than 5% of the population. So the first one is, they showed this down here, the sample. It looks like they took 6 in each. If you look at the mini tab output, this N here tells us what's in the sample. So they took 6 each. So N1 is 6, and that's less than 5% of the population. Okay. And then N2 is 6, and that's less than 5% of the second population. And this would be of the different players, of all the players in the American League versus the National League. And then 4 is either the populations are normally distributed, or the sample sizes are bigger than 30, or we're given the normal probability plot, and that's what we were given. So the normal plot looks linear. We got to go back to chapter 7 or so. Normal plot looks linear. So we can use normal. Okay. So the tests are below. You can see that they both say we're doing a 2-sample t-test. So the American League is mean 1 and the National League is mean 2. And we're testing to see if mean 1 is greater than mean 2, or the difference is greater than 0. That's the same thing here. Here is the sample difference between them. So it does appear to be positive. And the standard deviation, degrees of freedom, is calculated, a bigger calculation that we don't have to worry about calculating. And here's our p-value, 0.1066. So let's look at the questions. It says, how many American League teams were sampled? 6. What was the mean RPG for the American League? So the American League, they said, was mean 1. And that is shown in the mini tab, 5.185. So mean 1 was a sample 1, 5.185. And then it says, what was the standard deviation for the American League? 0.339. That's one is 0.339. And then D and E are comparing the sample sizes for each. StatCrunch sample degrees of freedom is 9.966, and then Minitab just says 9. 9.966, and Minitab just used 9. Okay. What was the average RPG difference? And we said that was 0.253. State the test statistic, that's the T. And that is 1.33. And that is the same in both. There's the test statistic there, and there's the test statistic there, 1.33. And the p-value is 0.1066. It looked like 0.1066 there, and 0.10, just a little bit different, 0.108 for the mini tab. So they're relatively close. Use a computer output to perform step 4. So I'm going to draw a curve. And because it's a greater than, we're going to shade to the right because it's a greater than. And my p-value is right there. And then J says if the researcher set alpha at 0.05, would the results be statistically significant? So this is essentially step 5, what we learned back in chapter 9. And the p-value is 0.1066, and the alpha is 0.05, and that's greater than. So we do not reject H0. So that means no, it is not statistically significant. Statistically significant. And K says, if the researcher set alpha at 0.05, what would we conclude? So there is not sufficient evidence to support the claim that the designated hitter rule affects the number of home runs. Okay. If the decision made above is incorrect, what type of error would you be making? So a do not reject means the type of error that we could do is a do not reject when H0 is actually false. So that would be a type 2 error. Just do not reject H0 when H0 is false. Okay. So we're going to look at example 3 and 4 are going to be using the little program in Desmos. Okay. So it says a study is done to determine if company A retains its workers longer than company B. Company A samples 15 workers and their average time with the company is 5 years with a standard deviation of 1.2. Company B samples 20 workers and their average time with the company is 4.5 years with a standard deviation of 0.8. The populations are normally distributed. So A says, are the population standard deviations known? No. So that means we're going to use the T distribution. Conduct an appropriate hypothesis test at the 5% level of significance. What is your conclusion? So our first thing, we're going to use our guide from our page in our formula packet, is stating the hypothesis test. So here are the 3 that we could be doing. And this is asking they think that company A retains workers longer. So they think that their average time with the company is going to be bigger. So we're going to say mu1 is company A and mu2 is company B. So I'm going to say H0, H1. So mu A is equal to mu B, right? That's H0. H1 is we think mu A is longer or bigger than mu B. Alpha is 0.05. And we're going to get our test statistic and our p-value from Desmos. Let's go there. So let's just write down our information we're going to enter into Desmos. We need our sample mean from A, which we need our sample size from A, which is 15 workers. And then an average of 5 years, and the sample standard deviation of A is 1.2. And then sample size of B is 20 workers. The sample mean is 4.5, and the sample standard deviation of B is 0.8. Okay. And the picture we're going to draw is a greater than, so our p-value is going to be over here. We're going to compare our p-value to alpha, and then we're going to draw a conclusion. So let's go enter this data into Desmos. So the program for Desmos is called two independent means. That's what you're going to be making sure you're using for this. Two independent means. So our sample size is 15. Sample mean of 5. Standard deviation of 1.2. The other sample mean was 20. And the mean was 4.5. And the sample standard deviation is 0.8. Okay. And the mean 0, we think the difference is 0, so we can leave that there. And then we're doing a greater than test. And there's our p-value. So our p-value is 0.092. And the t-value for this setup is 1 point right here, 1.3975. The difference between the two means, that z-score or t-score is 1.39, about 1.4 standard deviations above the mean. And so there's the, right here's our graph for that. I'm gonna go over here and grid this one. There it is. Okay, so let's go back and share a paper so we can finish this up together. So our p-value is 0.09. It's greater than alpha, so we do not reject H0. So that means there is not sufficient evidence to support the claim that company A retains workers longer than company B. Not quite enough evidence for that statement to be true. Okay, so we're comparing. So notice that we don't have a number that we're comparing to. We're comparing two samples to each other. Okay. So let's look at example 4. This says a study is done by a community group and 2 neighboring colleges to determine which one graduates students with more math classes. College A samples 11 graduates. They have their average at 4 math classes, standard deviation of 1.5. College B samples 9 graduates. Their average is 3.5 math classes with a standard deviation of 1. The community group believes that a student who graduates from college A has taken more, so a greater than again, than college B. And we're going to use a 0.01. So it says, is this a test of 2 means or 2 proportions? 2 means, because we're counting the number of math classes. Are the population standard deviations known or unknown? Known. So we're using the t distribution and complete the test. So we need our H0 and our HA is mean A equal to mean B. And we think mean A is bigger than mean B, college A, college B. And we're using alpha at 0.01 this time. And again, Desmos will give us the T and also our p-value. And again, we're going to just write down our summary information that we have. So we have N for college A and N for college B. So college A had 11 graduates, college B had 9. Sample mean for college A was 4 with a standard deviation of 1.5. College B had a sample mean of 3.5 and a standard deviation of 1. So that's what we're going to put into Desmos. So we're going to color in our picture. Again, this is a greater than. And then once we get our p-value, we can compare our p-value to our alpha of 0.01, and then draw the conclusion. So let's go back to Desmos and enter this information here. So we have 11, 4, 1.5, 9, 2.5, and 1.0, and it's still a greater than. So there's our p-value. Our p-value is 0.1997, and the t-score is 0.8899. So our p-value is pretty big. Again, it doesn't look like we're going to do any rejecting. So the p-value is 0.1997, which is greater than 0.01. So we do not reject H0. So there is not sufficient evidence to support the claim that college A graduates students with more mathematics. Okay, so just a recap, 10.1 is all about two samples, two independent samples. So two independent samples, quantitative data, and we do not know anything about their sample standard deviation. So catch me back for 10.3. Remember, we're skipping 10.2.